Welcome to the 11th and final preview video for Math S-322. The topic is the fundamental theorem of calculus. Though as you'll see in a minute, there are two different versions of this fundamental theorem. Let's start with version 1. This is the version that refers to the integral of the derivative of a function. To be precise, we've got a function g that's continuous on the closed interval from a to b, and I hope you're immediately thinking, aha, that's nice, that means it's both bounded and uniformly continuous, and differentiable on the open interval, and I hope you're thinking, of course the interval has to be open, we can't sneak up on a point from both sides to take the limit if that point is the end point of the interval. So this function is differentiable everywhere on this open interval, and furthermore, that derivative is integrable. You can't take that for granted because it's entirely possible that this derivative could be unbounded, which would make it non-integrable. But if all these conditions are satisfied, the integral of the derivative g prime from a to b is simply the difference between g of b and g of a. We can prove this theorem fairly easily by using the mean value theorem. So that's version 1, the integral of the derivative. Version 2 is the derivative of the integral. So we start with an integrable function on the closed interval from a to b, and on any subinterval going from a to x, the function is still integrable, and we can define an antiderivative capital F as the integral of little f over the interval from a to x. This version of the fundamental theorem then says the resulting antiderivative is a continuous function, and furthermore, at any point where the function we started with, little f, is continuous, capital F is differentiable, and its derivative is equal to little f. This proof doesn't use the mean value theorem. It uses the definition of the derivative, and it relies heavily on the assumption that except at certain isolated points, f is a continuous function. We can't prove that the derivative of capital F is little f, except where little f is continuous. So we've got both these versions. Where do we use one? Where do we use the other? Well, for making a list of integration formulas, we use version 1. For example, having noticed that the derivative of the tangent function is the secant squared function, we conclude that the integral of the secant squared function is the tangent function. We prove integration by parts. This proof will show up in class by applying version 1 to the rule for differentiating the product of two functions. To prove the change of variables formula, we need both version 2 and version 1. I always find change of variable easy to do in practice, but I have a bit of a hard time explaining it in principle. There are bizarre cases where you have a function that is integrable in spite of being discontinuous everywhere or almost everywhere. The standard example of such a function is f of x is equal to 0 for all irrational numbers, but for a rational number, where x is p over q in lowest terms, the function f is defined as 1 over q. This function is Riemann integrable. Its integral, in fact, is 0. So version 2 applies, but it says nothing useful about the derivative of capital F for the simple reason that the derivative of capital F equals little f only where little f is continuous, and this little f isn't continuous anywhere. Version 1 says nothing at all because you can't find a function whose derivative is this ridiculous little f. A weakness of version 1 is that if the function g that you start with fails to be differentiable at just a single point in the interval, the conditions for the theorem don't apply. And an example of such a function would be the 2/3 power function on -1 to +1. That's differentiable everywhere except at x equals 0. In this case, version 2 still works. It'll give us an antiderivative, and the catch will be that that antiderivative has no derivative at the point where the original function fails to be continuous. If you get into multivariable calculus, you will discover that there's a generalization of the fundamental theorem known as Stokes' theorem. I devote about 5 weeks in Math 23b to building up to this theorem, and this is ultimately a generalization of version 1. It's a theorem about the integral of the derivative. Now recall the requirements for a Riemann integral or a Darboux integral to exist. The function f that we're integrating doesn't have to be continuous, but it does have to be bounded, and we can only integrate over bounded integrals. Nonetheless, frequently in practice, you end up setting up integrals of functions that fail to be bounded, or setting up integrals over an interval that's unlimited in its extent. To deal with such cases, we introduce improper integrals. And let's consider first an example where there's a problem at the upper limit of integration, either because the upper limit is plus infinity, or because the function f is unbounded as we approach the upper limit. In that case, it's frequently possible to evaluate the integral from a up to some value d that's a little bit less than b. We can do that and then take the limit as d approaches b from below. That will give us a number, and we call that number the improper integral of f on the interval from a to b. Here are some examples. Ask one of your students to integrate e to the minus x from 0 to infinity. They'll do it with no trouble. Get the antiderivative minus e to the minus x. Plug in infinity at one limit and get 0. Plug in 0 at the other limit and get 1. And they say this integral equals 1. Indeed it does, but it's not a Riemann integral because the interval of integration is unbounded. Similarly, your AP Calculus students can quite likely evaluate the function x to the minus 1/2 from 0 to 1. They get the antiderivative, 2x to the 1/2, plug in the lower and upper limits, and come up with 2. But this again is not a Riemann integral because as x approaches 0, x to the minus 1/2 increases without limit. This function is unbounded. So these integrals exist, but they're not valid Riemann integrals. They're only improper integrals. Incidentally, it's also possible to make sense of both these integrals as so-called Lebesgue integrals. Lebesgue integrals, where they exist, are better than improper integrals because certain results do not hold true for improper integrals, but they do for Lebesgue integrals. However, that's a topic for another course. Where else could we have problems? Well, we could have a problem at the lower end point. That, in fact, was the situation with my example on the previous page, here we have a problem at the lower end point. What do? We integrate from d to b, and if we get a valid Riemann integral, then we can take that as a function of d and let d approach a and take the limit. We could even have a problem at both endpoints. To deal with that, what we do is split the integral up at some convenient point alpha in the middle of the interval where there's no problem. Then this has a problem at the lower end point, this at the upper end point, and we can deal with them both. Final topic, exponentials and logarithms. I managed to introduce the sine and cosine functions defined by their Taylor series and have a complete treatment of the major topics of calculus. We still need logarithms and exponentials. So here's a nice way of defining the natural logarithm function. We define it as the antiderivative of the 1 over t function. We integrate from 1 to y. Since the lower limit is 1, there's no problem with this t in the denominator. And then we define the number e as the upper limit for which the value of this integral is equal to 1. So this is all based on integration. Starting from this definition, we'll be able to prove very easily, using the fundamental theorem, that the derivative of this capital L function is 1 over y. And it's not too hard, though it takes a little bit of trickery, to prove that the natural logarithm of the product xy is the sum of the natural logarithms. Once we have the natural logarithm function defined, we can define the exponential function. We will define it to be the inverse function of the logarithm function. In other words, it's the function capital E, where e of L of y is equal to y itself. And now we can use our rule for the derivative of the inverse function to figure out the derivative of e. It will turn out that e prime of x is equal to e of x. And from this property of the logarithm function, we'll be able to prove that the exponential of the sum is not the sum of the exponentials, the product of the exponentials. I'm going to go back and fix the notes, but this is just a typo. That should be multiplication, and we are done.